Hey guys, welcome back to chapter 5. What we are going to talk about today is going to be probably one of the more difficult things we talk about this chapter. What we're going to talk about today is how these electrons get shared. So up until now, we've kind of alluded to the fact that, well, maybe they share them equally, but that's not always the case. That's not how it actually goes. All right, so let's look at this kind of anomaly, this funny little thing that happens, and then we'll go back and explain why it happens. So here we've got a molecule. It is covalently bound. It's a hydrogen bound to a fluorine. We see that 2 electrons are shared, and then fluorine has its other lone pairs. Okay. So let's say that these, they're called hydrofluoric acid. You don't need to know that. That's what I'm going to call them. Let's say these, hydrofluoric acid molecules are just kind of floating around in a beaker. So that's what we see in this first picture. And inside that beaker, we're going to slip 2 electrodes. So here we're just putting the electrodes into the solution. We haven't actually done anything yet. In this second picture, what we see is we turn these electrodes on, or we start to give it an electrical current. So here's our negatively charged electrode. Here's our positively charged electrode. And what we see is kind of a very interesting phenomenon, not something that we would predict. What we see is these molecules line up in a very distinct fashion. All of the hydrogens face this negative electrode. All of these fluorines face this positive electrode. So they align themselves within this electrical field. So what that tells us is there must be some sort of charge to these particles if they are in fact reacting to an electrical field. If they're just simply sharing electrons, we wouldn't expect them to react to an electrical field. We expect them to be neutral and kind of ignore the electrical field. But they line up in a very particular manner. So what's going on there? How do we get this kind of separation of charge? So the separation of charge is all about electronegativity. So electronegativity is the ability of an atom to attract electrons to itself. Okay. So some atoms make itself very, very attractive to electrons, and they kind of hog or attract the electrons' attention. Some of the atoms are like, meh, don't really care about electrons. They don't do any work to make themselves attractive. So when they're sharing these electrons, the electrons don't really go by them. Okay. So electronegativity is the ability to attract electrons to oneself. Here's a chart of electronegativity. So the numbers that were assigned were kind of an arbitrary number that was assigned. But what was assigned is that a 4 is the highest electronegativity. So that's over here on fluorine. And the lowest electronegativity would be a 0. Okay. So highest electronegativity is a 4. Lowest electronegativity would be 0. So what we're going to look at when we're looking at compounds is we're going to look at the differences in electronegativity. So somebody that has a high electronegativity is going to be very, very attractive to electrons. They're going to want to attract electrons. Somebody that has a low electronegativity is not going to be very attractive to electrons. So they're not going to, electrons aren't going to be attracted to that particular atom. Okay, and again, this chart is something that's available to you in the helpful handouts. It's something that I encourage you to just have maybe printed out or next to you, available to you as you're working through these examples, so you're not trying to hunt for it. If you were in the in-person class, I would give you a copy of this sheet right here. All right, so what we are looking at are bonds, right? We've been talking all about covalent bonds, the sharing of electrons. So how do we get this separation of charge that causes us to react to an electrical current within a bond where we're sharing electrons? So when there is an unequal sharing of electrons, when somebody's hogging the electrons and somebody's left without electrons, there's going to be a separation of charge, and we call this a dipole moment. So di meaning two poles. There's two poles in that molecule. So a dipole moment. There's a separation of charge, two different poles. So here we see a dipole moment within this bond between oxygen and hydrogen. So what we see is a very electron dense region over here by our oxygen. So in this case, oxygen would be hogging the electrons. And what comes with the electron? Well, the negative charge is going to come with that electron. So if this is an electron dense region, if this guy's hogging all of the electrons, there's going to be a little bit of a negative charge over here on this side of our molecule. Over here, we see what we call an electron poor region. So hydrogen is not very attractive to electrons. So if he's left in the absence of electrons, he's going to have a positive charge. So all of the negative charge went over here. So that means all of the positive charge is going to be on this side. So separation of charge. We call this a partial negative over here and a partial positive over here. Okay, so separation. Here we see the same thing. It kind of flipped over, but here we see an electron dense region over here with all the the yellows and oranges. Over here we see an electron poor region with the blues and the purples. So same kind of idea. Okay, so separation of charge. So what this tells us is that maybe these molecules don't share the electrons equally. So even though they are sharing electrons, they're touching 2 electrons or 4 electrons, maybe those electrons aren't being shared or touched equally. So the analogy that I always put forth here, I've got 2 little boys. I've got a 5-year-old and I've got a almost 3-year-old. So let's say we get a brand new toy for Christmas. And they're like, "Ooh, Mommy, I'm so excited about this new block set." Okay, with magnet blocks. And I say, "All right, great. Take these magnet blocks, go upstairs and share them. Make sure you share the blocks." "Yeah, okay, Mommy, we will." Those kids take the magnet blocks upstairs. Do you think they're sharing them equally? No. Who's hogging those blocks? Yeah, big brother is, right? He's either going to get more time with the entire block set, or he's going to take a bigger pile of the blocks and leave little brother with a teeny tiny pile. So are they sharing those magnet blocks? Well, yeah, they are sharing them technically. Are they sharing them equally? No, absolutely not. Okay. So there's a separation within those blocks. There's going to be a separation within these molecules. They're not sharing them equally. There's going to be a big brother who hogs the electrons, a little brother who doesn't. Okay. So to decide who's big brother, who's little brother, and are they sharing equally, what we're going to look at is their electronegativities. So we're going to take the electronegativities between 2 atoms. We're going to subtract those electronegativities and see just how large their electronegativity differences are. Okay? So let's look at a chart that's going to help us. All right. So we take their 2 atoms, we look at their electronegativities, we subtract them. If the number that we get from that subtraction is between 0 and 0.4, we would say, they're sharing those electrons equally. So we call this a pure or a non-polar covalent bond, okay? So they're sharing them essentially equally. If we look at the electronegativities, we subtract the 2 numbers, and it's between 0.4 and 2.0, we would say that that is a polar covalent bond. Somebody is big brother, somebody is little brother. Somebody is hogging the electrons, somebody's left without them. So unequal sharing, and we're going to see these polar regions, a partial negative on one side, a partial positive on the other. And if we subtract the electronegativity differences and it's greater than 2, so it's bigger than 2.0, what that tells us is that Big Brother is hogging those electrons so much that he just went ahead and stole the electron. So Big Brother went upstairs with the magnet blocks and he said, little brother, you just go sit and watch on that side of the room. I'm actually going to take all of these magnet blocks. They're not sharing them at all. Big Brother took them. So if an electron is transferred or taken, that's again an ionic bond. So now we have another way to predict an ionic bond. Okay. So let's look at some examples. So let's look at hydrochloric acid, HCl. So I'm going to go back to the electronegativity chart. And we're going to look at this bond right here, HCl. Okay, and we're going to try to determine what type of bond that is. Okay. So first things first, let's look at the electronegativities. Well, the electronegativity for chlorine is over here. That's going to be 3.16. Electronegativity for hydrogen is over here. That's going to be 2.20. So I'm going to look at the difference in those electronegativities. So I'm going to take 3.16 minus 2.20, and the electronegativity difference is 0.96. Okay. So I think this is going to be a covalent bond because I've got a non-metal bound to another non-metal. So probably going to be covalent. And if I look at my chart, I see the same thing. So this is going to be, again, 0.96 is the electronegativity difference. So that's going to fall in this middle region here. So that is going to be a polar covalent bond. So they're going to share the electrons. They're just not going to share them equally. Okay. So here's our bond. And remember, this had an electronegativity of 3.16. This had electronegativity of 2.20. So now we know they're sharing electrons. Now we know that it's an unequal sharing of those electrons. Now we need to decide who's big brother, who's little brother, who's going to have the partial negative, who's going to have the partial positive. Okay? So chlorine has the higher electronegativity, which means it does a better job of attracting electrons to itself, which means he's going to be big brother. So if he's hogging the electrons, with those electrons is going to come the negative charge. So this side of the molecule is going to have the partial negative. So this is a delta symbol here, and it's a negative. So partial negative. And hydrogen has the lower electronegativity, which means he's going to be little brother. He's not as attractive to the electrons. So he's going to be left in the absence of electrons, which gives him a partial positive. Okay. So big brother, little brother, partial negative, partial positive. And that's exactly what we see here. So chlorine would be the partial negative. Hydrogen would be the partial positive. There's a couple different ways to depict this scenario. So exactly what I walked through here with the partial negative, partial positive. You're also going to see these arrows. So as chemists, we're very, very interested in where electrons are going. So all of organic chemistry is following electrons. So we're always interested in where electrons are going. So we're going to have the arrow pushing towards big brother. Where are they being hogged? And then on the other side, we're just going to make a little cross, kind of helping us remember that that's little brother. That's a partial positive. So two different ways to depict this dipole moment. So what I want you guys to do now is I want you to work on an example. So determine if the following bond is pure covalent, polar covalent, or ionic. And I put this electronegativity chart here just because it fits on the slide with everything else, but it'll get you to the same answer. And then I want you to tell me if it's polar covalent, try to decide who's big brother, who's little brother, who's the partial positive, who's the partial negative. So go ahead and pause your video and see if you can work this out. All right, for the first one, electronegativity for SR is 1.0. Electronegativity for F is 4.0. So I'm going to subtract those, and it gives me a difference of 3.0. Yeah, it's negative 3.0, but when we're talking about the difference, we're going to take the absolute value of this. So you can always just change that to a positive number. We're just going to look at what's the difference? What's the magnitude of that difference? Okay. All right, so magnitude of that difference is 3.0. So what type of bond is that? Yeah, it's ionic, right? It's greater than 2.0. So it's an ionic bond. What's the other thing that told me this was probably going to be an ionic bond? Yeah, we've got a metal and a non-metal. So same story here. Metal and non-metal is ionic. Electronegativity difference greater than 2.0, ionic. Okay. Let's do nitrogen and chlorine. So nitrogen's electronegativity is 3.0. Chlorine's electronegativity is also 3.0. So an electronegativity difference of 0. So what does that tell me about this nitrogen and chlorine bond? It's a pure covalent or a non-polar covalent bond. They are sharing those electrons equally or evenly. So there is no dipole moment, no separation of charge, pure covalent. Okay. Let's do nitrogen and oxygen. So nitrogen is still 3.0. Oxygen is 3.5. So that's an electronegativity difference of 0.5. So electronegativity difference of 0.5 falls into the polar covalent region. So this is a covalent bond. They are technically sharing the electrons, right? But they're not sharing them equally. So in this case, who is big brother? Yeah, oxygen is big brother. So he has the higher electronegativity. So he's going to have the partial negative. And nitrogen, little brother, is going to have the partial positive. Or we could draw the dipole moment like this. So the arrow pushes towards the electrons. Okay. So in the next video, we're going to build upon this skill. So unfortunately, when we're looking at molecules, we don't just look at simple 2-atom molecules, right? We're looking at these molecules in 3 dimensions. So we're going to take this skill and we're going to put it into a 3-dimensional molecule. So at this point, make sure you're really solid on identifying the type of bond, because then we're going to look at what that looks like in 3 dimensions.